Hello dear students, welcome back to physics online class. So today we will be discussing another important aspect related to current, so that is heating effect of current. So in case of that heating effect of current, so for example, so treat this is one conductor. Whenever current is flowing through this conductor, then what happens here? This conducting material will get heat up here. Why this conducting material will get heat up here? So in case of that, so electricity, so whenever the current is flowing from that one edge to another edge, so these free electrons gets that thermal energy here. So because of getting thermal energy, this conducting material will get heat up here. So in order to consider this one, whatever the electrical energy I am supplying here, that electrical energy will converts into heat energy here. So that effect we can call it as Joule's law of heating here. So we'll understand about that, what is Joule's law of heating in case of electricity. So we'll understand about that. So heating effect of electric current. So in case of heating effect of electric current, heating effect of electric current, so we will understand about what's that mean of Joule's law of heating here. So Joule's law of heating. Okay, so in case of that Joule's law of heating here, so according to that Joule's law of heating, whenever that electrical energy means, or whenever that current is passes into that conducting wire, that electrical energy will converts into a heat energy here. While converting that electrical energy into a heat energy, whatever the amount of heat energy is there, so that amount of heat energy is equal to work done on the free electrons. So look at here, so that electrical energy is converted into a heat energy. I said that heat energy is equal to work done on the free electrons when constant amount of current is passes through a certain interval of time. So I will consider what is that work done value here. So look at here, in case of Joule's law of heating, so according to that Joule's law of heating, electrical energy converts into heat energy here. So I said that electrical energy converts into heat energy. Okay, so while converting that electrical energy into a heat energy, the quantity of heat, so whatever the heat energy is there, so that heat energy is equal to work done I will consider here. So look at here, heat energy is equal to, so I can consider that, so heat energy, so it is equal to work done on free electron, if constant current, so work done is equal to, so work done on free electron is equal to, so what that, so work done on free electron if constant current, so current is represented by symbol I here, so constant amount of current is flowing for certain interval of time, so that work done I can consider here. So look at here, from that electrostatic potential, shall I write that V is equal to what? W by Q. So W is equal to, shall I write it as a V into Q here? W is equal to what? V into Q here. So where Q is equal to what? Q is equal to I into T. I is equal to what? Q by T. So where Q, shall I write it as a I into T? So this one I can write as a V into I into T. So that work done is equal to what? Work done is equal to V into I into T. So that work done is stored it as energy. So I can take that energy, means that energy is equal to what? V into I into T. So that energy we can take it as electrical energy here. So look at here, electrical energy E is equal to what? V into I into T, where V represents that potential, I represents currents, whereas T represents that time here. I can rearrange this electrical energy in another form, so that energy I can write it in another form. So from Ohm's law, wherever V is there, so shall I write it as I into T? So wherever V is there, so just I can consider that. So in case of that Ohm's law, V is equal to what? I into R. So wherever V is there, just I will take it as I into R into I into T. I into I what? I square R into T. What is one more form for that electrical energy? That is I square R into T here. So from Ohm's law, so I got this equation, energy is equal to V into I into T here, where V is nothing but I into R. So if I do like so, I square R into T. One more form I can write it here. So from Ohm's law, I is nothing but what? V by R. So I square means what? V square by R square into R into T here. So here one resistance term will getting cancelled out. So E is equal to what? So E is equal to V square divided by one R term is there, V square by R into T. So these are all three forms of electrical energy. What are the three forms of electrical energy here? So in case of that electrical energy, so whenever that electric current is passed through the conductor, then conductor will get heat up here. So electrical energy converts into heat energy here. What is that formula for that energy here? Energy is equal to, what is that first equation? V into I into T, and one more equation, I square R into T, and another equation, V square by R into T. So these are all the equations related to electrical energy. What are the equations here for electrical energy? V into I into T, I square R into T, and another equation is V square by R into T. So these are all the equations for electrical energy. So now we'll look at about that. What is that electric power here? So what do you mean by power here? So power is nothing but rate of electrical energy dissipation, we can call it as electric power here. So we'll understand one more term here. So we are going to understand about that heating effect of electric current. So in case of heating effect of electric current, so first we'll understand about what you mean by that Joules law of heating. So from that Joules law of heating, we got that energy equation. So now we'll look after for that electric power here. So look at here, what is electric power then? I will represent by the symbol P here. The rate of electrical energy dissipation, we can call it as electric power. What is that electric power here? The rate of, look at here, the rate of electrical energy, the rate of electrical energy dissipation is known as what? So is known as electric power here. So I want to give that mathematical approach. So look at here, so electric power is equal to what? Energy by time here. So energy form is V into I into T divided by T. One more form, I square R into T, so divided by time, and one more form, V square by R into T, so divided by time. Here time term will getting cancelled out. And what are the required equation for power here? Electric power. Equation for electric power is P is equal to V into I. So remember here, so these equations are very much important for solving the numericals. So one more equation, so I square into R, so I square into R, one more equation, and another equation, so for power, so what is that? V square by R. So these are all the mathematical tool for that electric power. What is that electric power then? The rate of electrical energy dissipation, we can call it as electric power here. So now I can consider that whatever the electrical energy I said, that electrical energy I can express in terms of kilowatt hour. So look at here, by taking use of this formula. Power is equal to what? Energy by time. Shall I take that energy is equal to what? Power into time. So look at here, energy is equal to what? Power into time. So look at here, energy I will take it as power into time. What is the SI unit of power here? So power is nothing but watt here. So power we are going to measure in terms of watt. What is the SI unit of electric power here? So that is watt here. So SI unit for that electrical power here. So power we can consider in terms of watt here. So look at here. So power into time here. So power into time means, so power is nothing but in terms of watt. So time is in terms of hours I can consider. So look at here. So power we can consider in terms of watt and time in terms of hours I can consider. So this electrical energy I can express in terms of kilowatt hour. So in case of considering that kilowatt hour, 1 kilowatt hour I can take it as 1 unit here. So look at here, in case of that understanding about that electrical energy, we can understand that, so how much electrical energy will get consumed I can able to find out. So in order to find out about that electrical energy consumption, I can express in the form of kilowatt hour. So what is the SI unit of electrical energy? Kilowatt hour. So for example, to our home appliances, so we are getting electrical bill every month here. On what base they will decide the bill here? So we'll look after for that only. So look at here, energy is equal to what? Power into time. Power in terms of watt, so time in terms of hours I can consider here. So I can express this energy in terms of kilowatt hour I said. So look at here, if in order to express in terms of kilowatt hour means numerator and denominator I can take it as divide by 1000 here. Kilowatt hour divide by 1000 here. So this is the formula here. So this is the formula to find out that electrical energy here. So I can take that summation I can consider, or in general you can consider summation of watt hour divide by 1000 here. So we will get that energy in terms of kilowatt hour. Energy will get in terms of kilowatt hour. This 1 kilowatt hour I can consider as 1 unit here. 1 kilowatt hour I can consider as 1 unit. For example, in 1 month, how much unit you consume? So they will fix one rate here. So for example, if you consume 1 unit means, so they will decide that rate as a 7 rupee. For example, for 1 unit, they will decide the rate as 7 rupee. How much unit you consume, that electric meter will show that units here. So on that units, they will compare with the rate and monthly will get that electric bill here. So hope you are understanding. So we are expressing that energy in terms of kilowatt hour. So electrical energy we are going to express in terms of kilowatt hour here. So in order to express about that kilowatt hour, so for example, power is in terms of watt, time is in terms of hour, watt hour is there. So I want to make it as kilowatt hour. So numerator and denominator I can multiply and divide by 1000 here. So we are getting that energy in terms of kilowatt hour. So that kilowatt hour, 1 kilowatt hour I can consider as 1 unit here. 1 kilowatt hour is equal to how many joules? So look at here, 1 kilowatt hour. So 1 kilo means what? 10 to the power of 3. So 1 kilowatt means what? 10 to the power of 3 watt here. So hours means how many seconds it consists? So 1 hour means 3600. So 36 into, so I can consider this one as 36 into 10 to the power of, so 2 digits. So 36 into 10 to the power of 5 joules here. 1 kilowatt hour, it is equal to how much amount of joule here? 1 kilowatt hour is equal to 36 into 10 to the power of 5 joules. So look at here, we are going to understand that how that electrical energy means consumptions of electrical energy. In order to find that consumption of electrical energy, we are going to use this formula. So energy is equal to summation of watt hour divided by 1000. So if I do that watt hour divided by 1000, I will get that energy in terms of kilowatt hour here. So that 1 kilowatt hour I will consider as 1 unit here. So if 2 kilowatt hour means it will take it as 2 unit here. So they will fix the rate here. 1 unit if you consume means it will equivalent to 7 rupees here. So for 1 unit 7 rupees. How much unit you will consume? So that bill will get rise here. So we will make you understand about these electrical energy by giving one example here. So for example, so in our home appliances we are having 3 fan here. So we are having 3 fan. Each fan having that power consumption is 100 power here. Each fan will consume a power of 100 watt. How much power it will consume here? So it will consume 100 watt power. So it will run daily 8 hours. How many times that fan is going to run here? So in a day, 8 hours the fan will get run. Okay. So then after using that 30 days, so 1 month. So in 1 month, I want to calculate how much electrical energy is consumed. So I want to find out that in 1 month. So in 1 month means you can take it as 30 days. How much electrical energy is consumed. So I can take that 1 month means 30 days, and also find the bill. Find the bill if 1 unit it is equal to 7 rupee. So for 1 unit how much cost is there? For 1 unit, so 7 rupee cost is there. So I want to find out that how much energy is going to be consumed in 1 month. So what is the connecting formula I need to use here? So look at here. In order to express that electrical energy, so that electrical energy I will express in terms of kilowatt hour. So in order to express that in terms of kilowatt hour, so what is the connecting formula here? Energy is equal to summation of watt into hour. So how much watt is there? So each fan having that 100 watt. How many fans are present here? Three fans are there. So this is the connecting formula. Divide by 1000. So look at here. Watt is 100. So 3 fans are there. Each watt means each fan watt is means, so each fan having that power is 100 watt. So there are 3 fans. So 100 into 3. How many hours it will run? 8 hours it will run. How many days here? So in 1 month means I can take it as 30 here. Divide by 1000. Okay. So what is that? 8 into 3 into 3. 72. So 72 kilowatt hour. What is that electrical energy consumed in 1 month? 72 kilowatt hour. So this kilowatt hour is equal to what? Unit here. So 1 unit. So 72 unit here. So how much unit I will consume in 1 month? So if I run that 3 fans, each fan having that power 100 watt. So every day it will run by 8 hours here. So after 30 days, how much energy will get consumed here? 72 kilowatt hour. So then how much bill will get appear here? 72 into. So for 1 unit 7 rupees. So for 7 unit 72 into 7 here. So what's the answer here? So 72 into 7. So 504 rupees. So look at here. How much amount of bill will get appear after 1 month here? After 1 month I will get the bill as so 504 rupees. So this is the way to calculate that electrical energy consumption. So hope you are understanding these things. So now we'll look after for that. In case of that series and parallel combination of the resistance. So where the power consumption is more, I can able to find out here. So now we'll focus on power consumption in case of resistance. So in case of that resistance, so sorry, wait for a few minutes, dust is gone somewhere. Okay. Sorry. So I have to find out that power consumption in case of series combination of the resistance as well as in parallel combination of the resistance. What are the connecting formulas for the power consumption I said? So just I will list out the formulas here. P is equal to V into I, P is equal to I square into R, P is equal to V square by R. So these are all the 3 formulas here. So now I will take that applications related to heating effect of electric current. So in most of the time in competitive examination, they will ask the questions related to these corner. If two resistors are connect in series combination, then power consumption I need to find out. Then power consumption is given by, so I want to find out that power consumption. Then power consumption is, so for example, so I will take two resistors here. These two resistors having different value, and these resistors I will connect in series combination. For example, resistance R1 is equal to 10 ohm, R2 is equal to 100 ohm. So look at here, in series combination, which of the thing will be remains the same? So current is remains same. So listen here, I want to find out that in case of series combination, in which resistance we are getting more power consumption, I want to find out. So for that purpose, I consider two resistors, one is 10 ohm, another one is 100 ohm. So in case of series combination, current is remains same. So current is remains same means out of these three equation, which equation I need to use here? So here term I is there, current is remains same, I will take this equation. So I is remains same means I will take the equation P is equal to I square into R. So P is directly proportional to resistance. So power consumption is directly proportional to resistance. So it means that if resistance is more, power consumption is also more in series combination. So high resistance will consume high power. So out of these two resistance, so R2 value is more. So power consumption in R2. So P2 is greater than P1 if two resistors are connected in series combination. So look at here, if you consider two resistors, these two resistors if you connect in series combination, power consumption is more for high resistance. So what is the conclusion? So remember this point, power consumption is more for high resistance when high resistance if you connect in series combination. So look at here, if you connect that two different resistance in series combination, power consumption is directly proportional to resistance. It means that power consumption is more for high resistance in series combination. Now I will interchange. If you consider two resistance, if two resistance are in parallel combination, so look at here, second case I will take in parallel combination. So hope you are understanding these things. So in parallel combination, so for example, again I will take that same two resistance, and these two resistance I will connect in parallel combination. Hope you know basic things about that series and parallel. So R2 value is 100 ohm. So now these two resistors are connected in parallel combination. I want to find out that what about the power consumption, means where power consumption is more, I need to find out here. So look at here, in parallel combination, which of the quantity will be remain same? Potential difference is remains the same. So potential, sorry, so this one is potential is V, so this one is potential 0. So in case of parallel combination, so potential differences remains the same. So potential differences remain same means which equation I need to use here? So related to power and resistance. So this is the connecting formula. Here there is no term resistance here. So look at here, P is equal to V square by R. So I will use this equation, P is equal to V square by R, where in case of parallel combination means potential differences remain same. So P is inversely proportional to resistance, mean power consumption is inversely proportional to resistance in parallel combination, whereas power consumption is directly proportional to resistance in case of series combination. What it means here? If that resistance is more, so its resistance is more means power consumption is less. If that resistance value is less means power consumption will be more here. So in case of parallel combination, power consumption is more for low resistance here. 10 ohm is there, 100 ohm is there. So these two resistance are connected in parallel combination where the power consumption is more. So power consumption is more for less resistance. So power consumption is more in case of 10 ohm resistance. So what is the conclusion? I will get it here. So look at here. In case of that combination of resistance, so we are going to understand about that power consumption in case of series and whereas in case of parallel combination. So I got that conclusion here. What was the conclusion? I will get it here. So look at here. So power consumption is more for less resistance. Or low resistance you can call. So power consumption is more for low resistance when if you connect in parallel combination. So hope you are understanding these things. So remember this. So when the resistance are connected in series combination, power consumption is directly proportional to resistance. When the resistance are connected in parallel combination, then power consumption is inversely proportional to resistance. So how? Because so P is equal to I square into R. Current is remains same in series combination, so power is directly proportional to resistance. Whereas in case of parallel combination, P is equal to V square by R. So power consumption is inversely proportional to resistance here. So we'll look at some equations. So for example, if I am having that resistance, n number of resistance are there, those n number of resistance you can connect in series combination, then what is the power consumption I can consider here? If n number of resistance are in series combination, first I will take n number of resistance, first I will connect in a series combination. If n number of resistance are in series combination for same voltage, so remember here I mentioned that n number of resistance I will connect in a same voltage here. So then power in case of series combination is V square by n into R. Why I taken this equation? Why? Because so n number of resistance first I will connect in series combination, then I will connect in parallel combination for the same voltage here. So look at here. Here n number of resistance I will consider, that n number of resistance I will give connection to that of battery 5 volt, or if I take that same n number of resistance I will connect in parallel combination with the same battery. Here potential difference is same, means I will consider this equation P is equal to V square by R. So first I will connect in series combination, P of S is equal to V square by n into R. So then I will connect in parallel combination, then in parallel for same voltage. In both the cases I will take that same battery, means it has same voltage here. So power dissipation in case of parallel, so n number of identical resistance are connected in parallel combination, so that is R by n, so n into V square by R. So equation 1 and 2. So I will take that ratio here, power in case of parallel divide by power consumed in case of series here, V square by n into R, and so I can consider that V square by, first power in case of parallel here, n into V square by R, and in case of series here, so n into R by V square term will getting cancel out, R term will getting cancel out, n into n square here. Power consumption in case of parallel to that of series is equal to n square, or power consumption if that n number of resistance are connected in parallel combination. So power consumption in case of that n number of identical resistance are connected in parallel, So that is equal to n square times of power consumption in series combination. So what it means here in terms of statement I can say, so power n number of resistors are connected in parallel combination, then power consumption in parallel combination is equal to n square times of that power consumption in series combination. So this is about power consumption in case of that resistance are in series and resistance are in parallel. So remember that simpler thing is that if you connect that resistance are in series combination, power is directly proportional to resistance, means power consumption is more for high resistance. If you connect in parallel combination, power consumption is more for low resistance. Here power consumption in case of parallel to that of series equal to n square. And I can say that in another way, if n number of resistors are connected in parallel combination, power consumption in parallel combination is equal to n square times of power consumption in series combination. So